So our last tutorial today will be run by Hirst from Queen Mary University, and going to teach us how to compute metrics on Kähler manifolds.
More than up to that anyway. I've got this mic on you. Is the mic? Okay, yeah, I'm colorblind, so I can't see. Is that the right color?
It's green, yes.
Okay, can you hear me? Okay, nice. Great, I'll get going. So yeah, this is tutorial 2 for the string theory compactification course by Lara, James, and Magdalena. And yeah, I'm sure everybody's feeling very motivated for computing Calabi-Yau metrics now. It's definitely been hammered home how useful it's going to be. So this isn't quite that. It's going to be a warm-up problem ahead of Yidi introducing the Calabi-Yau metrics package in detail tomorrow. So to sort of set up for that, we're going to be doing this kind of first problem in solving some kind of differential equations on a complex manifold. So specifically, we're going to, as I say, it's a warm-up problem, so we'll start with the very simplest cases. We're going to start with CP1, and we're going to be solving some differential equations using stochastic gradient descent. And it's a nice warm-up for a few reasons. First of all, CP1 or tomorrow, we're going to be doing a big step with the CP1. We're going to replace by Calabi-Yau 3. The differential equations, we're going to replace it with this Ricci flatness condition. And the stochastic gradient descent, we're going to replace with some proper, more technical machine learning methods. As you can see, nice starter, lots of different ways to improve it. And yeah, I've coded this all from scratch, so hopefully you'll have a good feel for what's going on before using the package directly, which will be done tomorrow. So yeah, the comments to make. So this page I have up is my GitHub. This has the notebook on it to download from. If you're there, otherwise, if you go on the website or for the conference, it's on the program page at the very bottom of this. There is this also link as well to the GitHub, which has the tutorial. If you want to open that up and just download it to your system, so fairly straightforward. You just right-click on it or click on it and then download it. If you're not familiar with GitHub, but exactly this will give you the Python notebook. But a comment to add to that as well is that for the symbolic manipulation, I've used Sage. So just for people who haven't used Sage Math before, whereas Mathematica is great because it does a lot of symbolic manipulation. It has a lot more capacity than, or is used a lot more by mathematicians, because Python typically has these problems with numerical precision where we can't do things exactly. So to try and replicate that in Python, the package SymPy was developed. This had a lot of limitations. So in extending that, Sage Math is the extension of Python that has a lot of symbolic manipulation. So this is effectively like a kernel, as opposed to having a regular Python kernel. We're using a Sage kernel for your Jupyter notebook, but it does require downloading. It's not just a package that can be installed. So if you want to go to this website, I say at the top, this is just the Sage Math website, and have a go at downloading it. This takes a little bit of time. It's just run the install, which is, I'll give you a few minutes to have a go at that. And then, yeah, you can open a notebook from there. But if that ends up being difficult, there's no problem. There's a Google Colab equivalent called CoCalc, which is linked here. And yeah, this looks pretty similar to regular Colab for notebooks, and we can do everything in there. It's just slower. So if you want to have a go at downloading Sage Math properly, then that's even better. So yeah, before I go into the details of the notebook, if you want to just have a go at, I'll give you a few minutes to have a go at setting that up, and yeah, give me a wave or something if that isn't too clear, and I can come up and help troubleshoot. But yeah, otherwise definitely go for go for CoCalc if you can't be bothered or there are some obvious difficulties on your computer. Yes. Anybody had any success yet? Anybody need some? Okay, nice. Need some more time? What's the general vibe? People managed to open CoCalc otherwise. I'll give you a little more time. If you've managed to get it set up, yeah, just have a go at opening the notebook from that GitHub page, and yeah, just start having a quick read through it. If you like, yeah, we're going to be using yeah, functions defined in Sage, so that there's some nice documentation for how these are defined on top of usual Python stuff. So a few extra functions and things to learn for defining functions. Yeah, that's the unfortunate downside of Colab, is that you can't use the Sage kernel in Colab or import Sage. The limitation of Colab, unfortunately. Unfortunately not, no. So yeah, Colab is great, but it does have limitations that you can't, because Sage isn't a proper package, it's like an add-on. So you can't add it on to Colab. So yeah, but that's the whole reason they have this CoCalc. It's basically the same thing as Colab. This thing here, which you can go to with this link, looks identical, looks near identical, is good enough as Colab, but it has the Sage kernel, so it does the same thing if you're familiar with Colab and want to do it like that. Yeah, how are people doing? Any thumbs up? Anyone need any particular help? Okay, nice. Maybe I'll have a go at explaining the problem, and then when people get onto it, we can I can wander around and give people some help. So yep, this, as I was saying, this problem is a differential equation on CP1. So what specifically is that differential equation? So CP1 is in homogeneous coordinates parameterized by two complex coordinates, which I'm going to call, following James's notation, Z0 and Z1. So we know that there's this equivalence relation still for any lambda that's C star. So as opposed to just being the two-dimensional complex plane, there is this restriction from this identification which makes it CP1. This, I'm sure you've heard a few times in many iterations now over the last couple of days. But what I'm just effectively saying here is that we're going to still work in these homogeneous coordinates, but we're going to be aware that there is this extra condition. So we've still got two complex numbers, which is parameterizing our space. And our differential equation, or set of differential equations, I'm going to write up. So we're trying to find some function f, which is of Z0 and Z1. And we're going to model this function by some approximate, which I'll call a lowercase f. So the conditions, let me just write these up. So it's a set of them. So we have, in terms of differentiability, we want to split this Z0 and Z1 into the holomorphic and anti-holomorphic parts. So in reality, when we're doing our differentiation, we're really doing everything with respect to, we sort of have four real coordinates in a way, which are these. Which we'll be doing our differentiation with respect to. And that gives these. equations, which I'll take a minute to write out. Oh, great. Excellent. So these are our 4 differentiability conditions. So we have these for our f. I guess I could write that with a capital F as well, but either way, there's going to be some function of Z0 and Z1, which satisfies these conditions on CP1, and that's what we're looking to find. So I'm sure with a bit of intuition and some complex calculus, we could all do this by hand or just making some educated guesses at it. But the point is, we're starting with a simple problem. We're going to let the machine do it, and to find this solution, or to find this function which satisfies these conditions. So again, drawing parallels to what we're going to be doing with the metric stuff properly tomorrow. So what we are going to start with is some ansatz for the function style. And this is going to give us a set of coefficients within that ansatz, that, i.e. our parameters that we're going to be optimizing to represent the true function. So we're going to go under the condition that give me 1 second, let me just get that copied correctly. I'll get the coefficients names right. We're going to say our function not bar Z1 and Z1 bar is going to take the form check, get this right. I'm going to make this smaller so it fits on one line. Okay. Excellent. And yep, I have forgot to add squared factors on all these denominators. So just correct these. Okay, nice. All right, okay, re-summarizing. Oh yeah, sure, go ahead. Yeah. Yeah, you're right. Thanks. Yeah, exactly. So these are our differential equations we're trying to solve in Z0 and Z1 for this function f, which is going to be which we're going to be approximating by another function. We're going to start out with this ansatz, a very simple one at the beginning. And we have these four coefficients, which I label as a C with some indices. The one is because, actually, maybe let me say first. So because we're working on CP1, we have this homogeneous property of the coordinates. So that's why we're going to work with each combination on the numerator being some combination of holomorphic and anti-holomorphic, which matches the case at the bottom as well. Whereas, when we just write z's, just to refamiliarize that this effectively just means timesing it with itself, or timesing it with its conjugate. So we have this equivalent form in each case, all combinations of Z0 and Z1 bar, and then dividing by this norm of the two coordinates on the bottom. So we get something that looks very standard for CP1, equations in CP1. But what we don't know is what these coefficients are. We know they're going to be real numbers, but we want to find out which real numbers they are that lead to these differentiability conditions. So this is what this notebook is doing. So if you can have a look at the notebook now, I can have a quick talk through what the steps of the notebook are. So yeah, I guess any questions about brief questions about the setup or mistakes I've made to correct? Yeah? What does Yep. It's exactly the same algorithm, a very parallel idea. We're just going to be, instead of applying it to optimizing a loss function, we're going to be applying it to optimizing, or instead of applying it to optimize a loss, yeah. It's exactly the same thing. But now instead of the function being a neural network whose parameters are weights we're trying to optimize, the function is now this ansatz, and the parameters are these coefficients, and we're trying to optimize those. It's exactly the same way. To sort of give a spoiler for the process, we're going to be taking a sample of points, and then we're going to be sorting them into batches, and then we're going to be updating these parameters according to the batches we look at to best approximate this equation. So yeah, hopefully it'll become clear as we go through. Is that clearer now? Okay, good. Yeah. So is that it? I mean, good point to make. It's obviously most commonly heard about in neural network context, but here we're just using it directly, and we're starting with not a crazy neural network function to be approximating a metric. We've got a simple function that we're going to be by hand or hard coding directly. We're going to be updating it. So yep, this first cell here, this is effectively like a markdown cell. I'm just redescribing this problem. So it has these differentiability conditions again, which we've written up here. And this second cell, so yeah, a point to note, if you've got this up, this is what I was trying to say about you need a Sage kernel in the top right. So if you're doing this in CoCalc, you should be opening it with a Sage kernel as well, which should end up looking like this. You've managed to do that. If not, I'll just explain the first bit, and then you can give me a wave and I can help you get that set up. So in the first bit, we're just importing the libraries we need, nice and standard, also setting a seed, which you can set to none if you want to do it truly randomly. But I recommend for this first run through, we start with this random seed I picked here, 3, just for illustrative purposes. So feel free to run this as we talk through it, or if you are competent with Sage and want to, competent with what I'm saying, please feel free to just go through the problem at your own pace. If that's faster or slower, up to you. So yeah, this would just, again, just imports libraries, nothing too special, just gives us the extra tools we need. This cell here is now the point sampling. So the more, as you might think, we're hearing about the measures today, the better distributed the points, or the more we know about the measure of the points, and the more points we have, the better this, the more data we have to make this approximation better for the gradient descent. So what I've got here, I mean, as I say, just run it as it is for now. Here we're only going to be using 1,000 points, this 1e to the 3. We're going to be running some seeding. So again, this is just the pseudo number generator so that this first time round where we all have seed 3, everybody's getting the same points and everybody's getting the same seeding of the stochastic gradient descent, just so that it's easier for everyone to compare if you're doing the problem side by side. But then after this, we'll have a removing that. As James mentioned in this lecture in the morning, a good way to sample points, a good measure is this taking the normal distribution. So here, in this case, because we have effectively 4 real numbers, we have the real and imaginary parts of these 2 complex coordinates in the homogeneous space. So we want to take 4 random numbers times by the number of points that we're trying to generate. So per point we're taking on CP1, we need 4 real numbers, which is what we're doing with this line here. And then this second line here is then just going to normalize those points so that we have a position on the S2 sphere equivalently, or effectively we're just bringing them from general complex 2-dimensional complex space to CP1. And it's a uniform measure, so it's very simple and we're comfortable that that's going to give us a good set of points. This next line here then just reformats that into complex coordinates. So it's just the first number of the 4 we take as the real part of Z0, the second part is the imaginary part, and then the third part is the real part of Z1, and the last number is the imaginary part of that. So again, it's just reformatting these points from being coordinates on S4 into this CP1 setup. And then the final part of this is now going to be splitting our data. So I'm sure I missed the first few, but I'm sure with a good data practice of splitting our data set into train, tests, and validation. So the train is what we're using, the stochastic gradient descent. Validation gives us some kind of fairly independent measure of how the performance is improving during training. And then test is independent, used at the end just to verify the performance. So again, run this cell. This will give you your 100,000 points. If you want, add yourself another cell, and you can have a look at the points, sort of thing that we're getting. So again, this is Python. We work with floats, so we have complex floats, which is going to be our numbers we're working with, but we have 1,000 of these. Going on, so yeah, great. Point sampling done. We've got some points on CP1 to work with. Now going on to setting up our ansats. So this is where we really needed Sage, because the symbolic manipulation is quite subtle. So here, it requires symbolic manipulation in what we're doing. So this cell I've set up here if you run it, it will generate a Sage function, which if you see this line along the bottom, this has the form that I've written here. So it's just I've written it here because it's easier to read than straight at the bottom of the cell. But we effectively have 4 parameters, 4 real parameters that we're going to be optimizing to find the function that best has these differentiability conditions on CP1. So there is this max order 1 I've set is because we can generalize this ansatz to include terms that look like and then have this over terms that look like this, where the numerator and the denominator are then just a higher order. So instead of having 2 and 2, we then have 4 and 4. So there are these terms we can add in later. And because this is particularly hard for this part of the setup, I've added a functionality for that now. But yeah, don't worry about that for now. I'm just saying keep this max order as 1, and then one of the extensions that if you're interested in, you can have a go at is extending this to higher orders, which I can explain if you want to have a go at that. But anyway, now we have in Sage our function set up with the ansatz we wanted. And then our next step, our next cell, is going to be defining these differentiability conditions and defining the respective loss functions that we're going to be trying to minimize to satisfy or to find this correct ansatz. Apologies. So again, now I'm just setting up as functions these differentiability conditions. So each of these 4, this top of this next cell, I've hard-coded in directly with this Sage conjugate function to denote conjugates. And then below this, I'm defining 4 losses for each of the parts of this differential equation difference that we're okay. Okay, great. So we have this f here. If I were to be looking at this equation here, then yeah, I've written these f's the other way around, but if I was to do df dz1 bar minus, I called this equation A minus the A, and I want this to be as close to 0 as possible, such that when this function, this ansatz function, is differentiated in the same way, it's going to have, all the point set we're looking at, it's going to have the exact same differentiability behavior. We want this to be as close to 0 as possible when we're optimizing. So that's what these losses are. In fact, so here, this function, I've done the f's the other way around in the notebook. So let me just correct that to avoid notation confusion. Okay, cool. So then, yeah, each of this loss A, B, C, D, these are these four conditions. So in each case, when we have we start from initial point, which is going to be, say, I don't know, 5 in each of these cases. So these coefficients are going to be evaluated. We then differentiate that function at the set of points we're considering in the batch, and then compare it to this equation, evaluate it at those same points, and we want these to line up as well as possible. This is how we set up this loss. So here I'm just doing that for each of these equations, adding those up. There is a simplify function, which is heuristic and not excellent, but it can simplify how these how functions in Sage look. So I've added that on as just a good measure for being able to read, and maybe some speed as well can be improved as the equation is simpler. And then there's loss functions for just evaluating if we wanted to sub in the constants and the points into this total loss. There's a function that we can then call to do that. The next part of this cell is then the other thing we need in stochastic gradient descent. So when we are updating so effectively this space we're moving in, so we have these coefficients. You can sort of think of this as maybe some real 4-dimensional space, and there's going to be an optimum position, an optimum point in this 4-dimensional real space where we have these conditions satisfied. So when we want to find out a good step direction to take, we need to find out how this loss function, the sum of these, is going to change with respect to steps in this 4-dimensional real space, steps in this coefficient space. And that's what this loss gradient function does. Just analytically, or this gradient function we do first, it does this differentiation with respect to each of the coefficients. So you take the grad with respect to what we're trying to update, and then we substitute in and then again, there's a function to substitute in the actual constants and the actual points that we're at in the batch to get to the gradient direction that we're going in. There's some problems. Will work. Okay, great. So yeah, again, this is something to run if you've been able to do this live. At least you can watch me as well. And then all I've done is just run a quick test example for you to have a look at as well. So I'm taking an example set of coefficients. So evaluating each of these as some real numbers. Yeah, I've just picked integers, and then evaluating at a specific point as well. And then this is what this is evaluating at. These coefficients at this point, this is what the loss evaluates to, the difference in these differentiability conditions for all of them summed. And this is what the gradient says. So it says if we wanted to change these coefficients to a set of coefficients that minimizes the loss, i.e. we want to update this ansatz to be closer to the true function, then we need to change these we need to change the coefficients in these directions, or effectively the negative of these directions if we're taking the maximum gradient. But you can think of it as we would actually be taking the negative of these, but this would mean we'd be adding 0.1 in this direction to increase this first coefficient, minusing 0.12 to decrease this one by the same amount, and decrease this one by 0.118 as well. So just to give you a feel for what this loss and this loss gradient is doing, it's giving us some information about what the losses evaluates to for specific coefficients and specific points, and then also what direction it gives the greatest increase in the loss. So we just take the negative of that to get the decrease. And the trick is that now we have these as functions. We're going to be evaluating this at loads of points in batches across all this data set that we've set up. And this is what is done in this final step here. So this is the actual stochastic gradient descent. So here again, we seed like normal. We're going to initialize the coefficients to 4 random numbers. And then, yeah, it's going to output the coefficients so we can see them. We again have some hyperparameters for our stochastic gradient descent. So when we're computing this loss gradient, we're going to do it over 32 points and then average those to get us a more logical, instead of being so erratic, we're going to get a more consistent step because we're doing some averaging over the points. We're going to run this stochastic gradient descent for 10 epochs, so over the full training data set 10 times. We have a learning rate of 0.01, so this is instead of taking this full step size of the gradient, we're going to just scale it down to 100th the size, so we don't take massive steps, we're just doing little bits at a time. And then there is these extra factors there's a tolerance, so when the loss is below a certain level, we're just going to stop, we're not going to run to the end. And there's this momentum, which I can come back to talk to in a bit, but this is a start of some extensions that you can have a go at that will hopefully improve the stochastic gradient descent if you want to have a go. So then here we're just going to repeat for the number of epochs. So an epoch is running over all the training data. So we're just going to see the training data in its entirety 10 times. But importantly, this is where the stochastic part of the gradient descent comes. We're going to shuffle this data each time we start a new epoch. So i.e. the batches are going to be different splits of the data each time. And this is where the stochastic part comes into the algorithm. We're then going to run over batches of the data. So we said we're splitting it into 32s. So for example, our case, we started with 1,000 data points. We took 70% of that as our training set, so 700 points. And then we're going to split this into batches of 32. So whatever 700 divided by 32 is going to be the number of batches. So for each batch, we compute the loss to just save to keep track of our performance. We compute the gradient, i.e. which direction in updating the current coefficients is going to minimize the loss for this batch of points. And then we're going to take a step in the opposite direction to minimize the loss, which is what's done here. And there's ways to vary this in the extension to be more technical. We're keeping track of some tolerance. So if we end up, there's no improvements to the loss, there's no point in continuing to run. And then we're going to take the step, and then the rest is just keeping track of this loss as we run through. So let me run this. Brilliant, good timing. Okay, so we should come back. Okay, great. So it did run quite nicely, but it ran in the meantime while I was off screen. So yeah, you can see I kind of had it to print in a pretty way so we can see the progress, and we see the loss starts at 32, goes to 17, 10. So it's slowly going down as these coefficients at the end of each epoch are updating to more sensible coefficients. In this case, they give us a better function that better satisfies these conditions. And at the very end, we get these coefficients at the end, where we know these, or at least the ansatz I'm telling you, these coefficients are going to be integers. So we just can do some rounding to the nearest integer, and we get these numbers 0, 0, 1, and 0, which is brilliant, which is what we're looking for. So yeah, it's kind of a start to finish. Description of running some stochastic gradient descent on a function ansatz to try and satisfy some differentiability conditions. And just to validate what we've seen here, the pretty loss graphs that everybody likes to see, here we have just a display of how this loss was reducing per epoch during the training process for both the training data, which is actually using, and this validation data, which it doesn't use for the training, but is just evaluated throughout the training process. So, okay, yeah, so exactly. Depending on the ansatz that we start with, we could definitely just use floats here as well, or just any numbers. But what I probably should have told you at the start was the secret function that I've given you actually does have these as integers. So at the end, we're using this approximation as real numbers to perform the gradient descent. But at the end, we just want the integers, so we just take the integer part. But yeah, exactly. We could have started with a problem whereby this hidden function I haven't told you actually has rational numbers or whatever, or any kind of other non-integer number in here and run the same problem. Yeah. Yeah, it is quite off, exactly. So the point is that this stochastic gradient descent is the most simple thing you can do. There's lots of ways to improve it. There's including the momentum, which I maybe hinted at a bit earlier, which effectively keeps information about the previous steps you do. So steps in previous batches. This is a way to improve your direction. So it continues updating along a more consistent path to the gradient descent. There's adjusting your learning rate. So when you get very near the end, you probably want to take smaller steps because you're likely to be closer to your minimum. So this is something you can do. There is other characteristics where you can make these reductions exponential in a way. This develops these stochastic gradient descent into popular algorithms like RMS prop or ADAM. So these are another extensions I would highly recommend in the rest of the time to have a go at implementing yourselves to try and improve, as you say, this very simple stochastic gradient descent to a better method. So yeah, this is the basis of the notebook. At the very bottom here, I have a list of extensions for you to play around with yourselves. Some of these I've done, so I can, if you're really interested in it and then get stuck, I can give you the code to play around with. But I definitely have a go at doing them yourself. First things for sure is to go back to the very beginning and trial with different numbers of points. trial with different splits of the proportions, trial even with different seedings, so these different coefficient, or effectively what I'm saying here is trial by setting these coefficients you start with to specific numbers, either really close to the solution you want to work with, see what happens, or maybe stupidly far away, see what happens with that. To see how this algorithm changes based on your starting points, your sampling, whether your sampling is really high or really low, and then changing your parameters of your gradient descent too. Have a go at that. That's definitely the first couple of things I would recommend doing as extensions. They're quite nice, self-contained within this problem. And then, as I say, you can update this momentum to be accumulated and develop it into proper, commonly used optimizer methods like ADAM or RMSprop, if you'd like to. So you can Google that, and the equations aren't too heavy, but it just requires a little bit of extra variables that you use to keep track throughout your training. Other extensions to have a go as well are described here, extending your losses to higher orders. So here I've specifically used the norm of the difference here, but we could do the square, the absolute value of the difference, the cube of the difference, those kinds of things. So more things you can change to see if the performance improves. And then, yeah, something interesting, which I think if you play around a bit will be definitely worthwhile implementing, is some regularization. So this problem actually ends up being a really nice motivation for regularization, which, yeah, if you have a play around, hopefully you'll start to see. And then exactly beyond that, there's lots more extensions where we can improve this ansatz to be higher orders. If you want to play around with the maths yourself, you can start with a function that of your own design, which follows this ansatz form to higher orders, and then compute these yourself, hard code those in, and try and learn that as well. But yeah, exactly. Effectively, this was the base notebook for stochastic gradient descent to solve differentiability conditions in complex manifolds. Please, yeah, have a walk through, get familiar with this notebook, and then start having a go at coding some extensions yourself. I'll just kind of float around and help people who need help with anything, or just chat about the problem and what would be interesting ways to extend it. Cool.
Is there anything you want to do before? No, exactly.
Yeah. But let's finish up. Just finish. So